We're now going to look at examples of how we can apply natural deduction rules as we have learned them. So we'll start a little bit simple, then we'll escalate the level of difficulty as we proceed forward. Right. So you will get something like this, for example, for 6 marks, right? So it's saying you're given not P, negation of P and Q, the negation of this. You're given P is true, and you want to prove not Q. Right. So before you attempt or you start writing down a proof, you need programmers who have what they call a pseudocode, right? A structured approach of how you're going to deal with the problem. So you sort of need to solve the problem before you even start writing down the solution, right? So how many ways are there of proving not Q, right? So we saw that if you want to, one, we've got proof by contradiction. What will proof by contradiction say? It will say that you start by, so you've got what you're given, your premise P and Q, and you've got P. These are your premise, right? I'll explain what I'm doing in a bit, right? From here, to prove not Q, I can assume that not Q is true, right? If I were to reach a contradiction here, it would mean that I can conclude that not Q is true. And this would be proof by contradiction. Right? That is number one. Right. Then number two, I can assume that Q is true. Right? If we have Q, we can assume that Q is true. Say, for example, if you have got Q or not Q, right? If Q or not Q is true, which is LEM, you have got P. You can then say this is disjunction elimination, something we're going to do in detail on the next examples. I've got Q. I can assume Q is true. And then after that, because I've got P is given to be true already, then I can have P and Q, right? Then I'll also need to prove P and Q from, so this is not complete here. So over here, I can prove P and Q, right? But this is now a contradiction with not P and Q. I'll get to a contradiction and I can then prove not Q. Or if I were to assume not Q, because the assumption is what I need it to be, I can simply conclude not Q as well. And that is a rule called copy or reiteration. So from Q, I've proved not Q. From not Q, I've proved not Q. Therefore, not Q is true. Now, this is now mainly coming from practice and experience, knowing how to massage my way around these, right? But then for the purposes of this, let's look at proof by contradiction, which is the much more probable one to use. So we're saying in our proof, we're going to have rows or lines. Each line will be numbered or indexed, right? You don't have to draw these lines, but for the purpose of this, each and every row you write must be indexed, because we will refer to which row was used in each and every rule that we choose to use. So the given are called premise, so we label them. We say they exist in this space because it is a premise. Now from here, we say we want to prove not Q, so we can assume the negation, right? Let's assume the negation. So let me start by removing this and proceed. We can assume the negation of not Q. So we want to get to not Q, we assume it's negation. So what is the label that I'm going to write here? This is an assumption. I've opened what I call an assumption box. This is assumption box. Number 4, I'll then say I've got negation of that. I can remove this double negation. So I have Q, and this will be double negation, elimination. Where did I apply it? I applied it on line number 3. Right. Then now I have got Q. I have P already. So you see here that this whole subproof or assumption box is nested within my main proof. So everything that is true in my main proof is also assumed to be true in my subproof. So if P is true here in my main proof and I've proven Q to be true here, then P and Q can be true, right? Conjunction is true if both the inputs are true. It's true here, it's true there, therefore it is true. So we say that this is conjunction introduction. On which lines? On number 2 and number 4. Number 2 and number 4. Right. Now we've got P and Q, and we've got the negation of P and Q. Number 6, we reach a contradiction. What is that rule? It is called negation, elimination. And where have I applied it? On number 1 and number 5. Right. Once I have this, I can close this subproof. I can close this subproof. Now, the conclusion of this subproof is written outside of the subproof. We saw that, I believe, when we're doing the rule, it said notify, and then you reach the conclusion or contradiction, then you can, outside of this, you conclude whatever it is you want to conclude. So outside of this, negation out, we are remaining with this, so it becomes not Q. This is proof by contradiction. And this included this whole subproof to prove. So it's from number 3 to number 6. Once you get here, you stop. You have arrived at the solution. All right. So this can fall away now so that you can have the full solution. Let's look at another example. A little bit more complex this time around. So the only way you can get through with this, the only way that you can fully understand it is by practice on your own as well. Right. So over here, we are trying to prove not P. Right. So you will realize that statements like these or proofs like these, where you are proving a negation of something, right? Proof by contradiction always works out well. So we have got there, we have got number 1. Number 1, we are going to have P and Q implying R. This is a premise. Number 2, we're going to have R implies S. This is also a premise. Number 3, we're going to have Q and not S. This is also a premise. All the premises are done now. So number 4, we now need to find our strategy. So if we assume P here, or not P, and then we get to a contradiction, we should be fine. So let's start there, right? So assume negation of P, assumption. Okay. Then number 5, we are going to have P is a result of double negation, elimination on number 4. Then number 6, we're going to have, we've got P, right? And nothing else. We've got P and nothing else. What else are we looking for, right? What else are we looking for? So we've got P implies if we had, for example, if we had Q, we can have Q, P and Q, and we can then have R. If we have R, we can use implication elimination. We're going to look at all these rules. We can have implication elimination and get to there. So for us, for this to work in the way that we want it to work, we need a queue of sorts. We need a queue of sorts. So say, for example, we introduce the queue and we say Q or not Q. Right. That is LEM. The number 7 would then say, we've got P, we've got Q, so we start with Q. This is now disjunction elimination. We've got a disjunction we're eliminating. We start with one side, it's an assumption. Then number 8, we've got P, we've got Q, we have P and Q. That will be conjunction introduction on number 5 and 7. If you have P and Q, then you can have number 9, you can have R, right? And then this is as a result, P and Q, we said we've got, if you've got P implies Q and we've got P, then Q is true. So we've got this is true and we've got this individual is true, therefore R is true. So if implication elimination on number, where is the implication? Number 1 and then number 8. Then if we have R, remember our goal is to prove a contradiction so that we get to not P. Okay, so if we've got R, we can have S. So that's implication elimination again. Try and see if you can figure out. I'm using R implies S in this R, and then I'll have on number implication elimination on number 2 and number 9. Number 9. Right. And then because I've got Q and not S, right? I've got Q and not S, I can have not S, and this is conjunction elimination. It will give me conjunction elimination position 2. It will give me on number 3. Then I can sit. So this will lead me to a contradiction. And this contradiction is negation elimination on number 9 and number 10. Right. So that is where we are so far. This is number 11. Then number 12, we'll start by assuming not Q. Right. If we were to assume not Q, we're going to have a contradiction because this has got a Q. So we've got Q and not S, so we're going to have number 13. Q, this is an assumption. And then Q is what? Conjunction elimination position 1 on number 3. And then we have a contradiction. And then we this is negation elimination number 12 and 13. Right. So we have Q or not Q. From Q, we've managed to prove a contradiction. From not Q, we've managed to prove a contradiction. Therefore, a contradiction is true. This is number 15. And then this is disjunction elimination. What statement was the disjunction? Number 6. And then the first subproof is number 7 to 11. The second subproof is number 12 to 14. Right. Then we can close the subproof of we've achieved our goal of proving a contradiction starting from double negation elimination. Then number 16 would then say we started here, we added there, therefore this falls away. Negation of P is true, and this is proof by contradiction. On number 4 to number 15, that was the whole subproof that showed proof by contradiction. Right. So that is the way we would go around doing it. Now, is there another way that someone could have used? Possibly, right? Possibly. Let's see, is there another way? I could have, for example, start with number 1. I've got P and Q implies R. I've got number 2, R implies S, and therefore number 3, Q and not S. So these are all premise, premise, and premise over there. So number 4, I've got a disjunction here, or conjunction. So I can have Q is true. So this is conjunction, elimination, position 1 on number 3. The number 5, I can have not S is true, conjunction, elimination on number 2. This is straightforward. Right. Now, if I were to do this, I've got Q. Even if I then go and open an assumption box for negation, negation P, like that, which becomes P, after double negation, elimination on number 6, I will have P and Q. I can have P and Q, right? This is conjunction introduction on number 7 in number 4. Then we can have number 9. If we have P and Q, we can have R, and that is implication elimination, like we did last time, on number 1 and number 8. And then we can have S as well, and that's implication elimination on number 2 and number 9, right? So once we have this, we have got S and we've got not S, therefore we have got a contradiction, right? We close the subproof, it's negation, elimination on number 5 and number 10. And then from there, we can have number 12, which will be negation of P, which will be proof by contradiction from number 6 to number 11. So here we've got 12 lines. On the previous one, we ended up with 16 lines. So depending on how you do it, it can be done faster and easier, or it can be done longer, still easier. Right? So what I'm trying to show is that there's no one way of doing things. There is no one way of doing things. And that brings our discussion to an earlier point made to say that that question that asks for the appropriate tool to use when proving that a argument is not valid cannot be natural deduction rules. Right? The fact that you fail to find a pathway, you as a person fail to find a pathway from the given to this, does not mean that that pathway does not exist. There's no way to comprehensively prove that all the paths for this, there's no path, because you need to try a million different possibilities, an infinite number of possibilities before you can do it. Especially now, because you've got a rule like LEM that can keep on introducing P or P or not P, Q or not Q. It can keep on introducing infinite amount of new lines to work around. All right. So that is it. Let's look at more examples in the next slide.